Hello everybody, this is Mr. Zabo. This is linear programming take 2. This time we are going to talk about a function that we are going to minimize. In this case, minimizing cost. So this is an airplane company. They are producing two different types of planes. They have no more than 40 flying bats that can be built each day, and no more than 60 flying falcons can be built each day. That is going to be key in writing our constraints. Also, there are enough workers to build at least 70 toy airplanes each day, so again, there's a constraint. It costs $12 to manufacture the flying bat, $8 to manufacture the flying falcon. How many of each plane should the company produce each day in order to minimize cost? So again, start by defining variables, write a cost function in this case because we are going to minimize cost, so we're not worried about profit in this function, and then identify our constraints. If you want to try now, go ahead and press pause. Before you do that, just know that I'm going to be using these as my variables I've defined because I have to know how many of each plane they should produce, so I need to know the number of flying bats and number of flying falcons, and I'm going to use these X's and Y's. Go ahead and press pause now if you want. You can try to come up with your cost function, which will be your objective function, and then come up with as many of the constraints as you can. So our cost function, 12x plus 8y, is going to represent our cost since it's $12 to manufacture flying bats, which was x, and $8 for flying falcons, which was y. Here are our original constraints. Our constraints represent that we can make no more than 40 flying bats, no more than 60 flying falcons, and that a total they want at least 70 toy airplanes each day. The only constraints I don't have on here right now are the implicit constraints, and that is that we do have to have x and y greater than or equal to 0. You will oftentimes see that written as compound inequalities this way to represent our quadrant 1 or our implicit constraints. So now I'm going to go ahead and ask you guys to take these constraints and try to plot them on the coordinate plane. Again, recognizing that what we're focused on is quadrant 1 because of those implicit constraints. You can try to use Desmos, or you can try to graph those on your own. Our x's in this case are representing the flying bats, and our y's the flying falcons. Here is how I have scaled my graph. I went up by tens in the x and the y, labeled each axis. If I look at just our first two constraints about the number of flying bats and the number of flying falcons, my feasible region is in here, but then I also have to graph my last constraint. Now this would represent the line for my last constraint, but again, 0, 0 is not part of that solution set, so the origin is not. Also, I can look at it as a greater than. I'd have to shade above that line, which means the only overlapping section here is this triangular region that becomes my feasible region. So that's the region that really gets shaded in or colored in, however I want to determine what that looks like. That becomes my feasible region. I have 3 vertices, 1, 2, and 3. Those are the 3 vertices that I want to check. 10, 60. I want to check 40, 60. And I want to check 40, 30. Plug all 3 of those into your cost function. So for these 3 solutions, we have a cost of $600, $960, or $720, which means this solution set represents the minimum cost. So we would answer this by saying that the minimum cost of $600 is achieved when we sell, or when we produce, 10 flying bats and 60 flying falcons. That would be the work representing our answer, and this is what we would be expected to write as our final answer. Or something expressing the same thoughts here, mentioning what the minimum cost is and what it would take to get that.